All right, ladies and gentlemen, welcome back. This is going to be your AP Chemistry Kinetics Lecture 5.6. We're going to be discussing reaction mechanisms. Today, we've got a set of learning objectives. Make sure that you can, or you pause the video, go ahead and take a second to read those so you can frame what you want to pay attention to here. And let's move on. Okay, so we're going to be looking at reaction mechanisms, and essentially, reaction mechanisms is a series of individual reactions that add up to an overall reaction. And this is something we've seen before, guys, when we've been looking at like these sub-reactions for calculating enthalpy, for calculating Gibbs free energy, for calculating entropy. You know, we have these series of reactions that essentially add up to some overall reaction, is what we're going to be looking at here. And what we're going to call these is we're not going to call them sub-reactions anymore. The vocabulary you're going to need to know is we're going to call them elementary reactions. And essentially, an elementary reaction is something that can't be broken down any further. So an overall reaction, we can break it down into simpler steps. An elementary reaction is the simplest that it can be. We can't break it down any further. There's nothing going on inside of it or around it. It is what it is. And so you need to really make sure you pause the video and write down in your notes and you distinguish between the difference of an overall reaction versus an elementary reaction. In an overall reaction, we can break it down into simpler reactions. We can get sub-reactions or elementary reactions for it. And the elementary reactions, they are the simplest that it can get. We can't break it down any further than what it is. And so that's what we really need to get on this particular page. We need to understand what a reaction mechanism is. We need to know what an elementary reaction is, and we need to know the difference between an elementary reaction versus an overall reaction. All right, so here's a specific example, and I've got these two are elementary reactions, and I'm just going to put ELEM, and then here's my overall. So that's my overall reaction. And so notice my elementary reactions add up to my overall. Again, this is something that we've seen before. And so I've got some species that's going to form some products, and then these products are actually going to be consumed in the second one, in the second elementary reaction, and then they're going to form your products. Well, notice if I add these up, I actually end up with my overall. Now, something I definitely need to point out here is this HI. Notice it's formed in the first reaction and then consumed in the second reaction. And by definition, that's what a reaction intermediate is. And so let's go ahead and put this definition down here. This is going to be produced in one elementary reaction and consumed in another. All right, and so our potassium, or our hydrogen, I'm sorry, I can't talk right now. Okay, so our hydroiodic acid, which is HI, right? We've got HI here and HI here. It's produced in one, it's consumed in another elementary reaction, therefore it meets the criteria of being a reaction intermediate. Another thing that we want to get into play here, and I'm going to go ahead and write something here. Let's assume that for these elementary reactions, I've got one that's slow and one that's fast. And so let's think of the bottleneck scenario where if I've got two different reactions going on here, one of them is going to occur relatively slow, the other one's going to be really, really fast. We have to start thinking about which one of these is actually going to determine the rate of this overall reaction, right? Because this reaction can't occur faster than its slowest step, right? So this reaction, this overall reaction, cannot occur faster than its slowest step. And so what we're going to do is we're going to start looking at that logic and saying, hey, if that's my slowest step, my reaction should be based on that. And we can actually get to these these elementary steps, and we can start determining rate laws just by looking at a balanced equation. And then we can actually use experimentation to either accept or disprove our overall rate law. All right. And so in this particular case, we would just say that this, and we're going to get into this in just a second, so I'm not going to get too far into it, but just understand that with any elementary steps to add up to an overall reaction, we're going to have slow and fast, and we'll start looking at these slows, and these are going to be what are called our rate limiting steps. All right, so it's important to understand that the slow elementary reaction will become our rate limiting step. All right, and so in here, what we're going to do is we're going to look at the different types of elementary reactions that we're going to run into, and it's all essentially based on how many molecules are involved in that elementary reaction. And there's three major types that we're going to look at. That we've got just A going to products. This is a unimolecular, and again, it's uni because there is only one. We've got A plus A to give me a product, and that's going to be a bi, or A plus B, and that's a bi. So if I have two reactants coming together to form a product, then it's going to be bimolecular. And then termolecular is when I have three or more three products, and that's going to be my termolecular reaction. And here's what we need to understand, that once we get past this point, these don't happen very often. Right? And go back to the collision model that we went over in 5.5, the likelihood that three different molecules will come together and collide in the specific orientation necessary and with enough energy necessary to actually form this product is actually really, really low. And so our termolecular and beyond, they really don't happen that often. And so we're not going to really worry about them. We're going to be focused more on unimolecular and bimolecular because these are the ones that are going to occur with some level of frequency so that we can look at. And then another important thing is that here the rate laws, since the only thing inhibiting these reactions is the concentration and physically these molecules running into each other, for an elementary reaction, the rate laws are proportional to the coefficients. And so rate laws are, and put it down here, are proportional to coefficients. And this is only for elementary reactions, guys. It's only for elementary reactions. It's only for elementary reactions because the only thing inhibiting or allowing the reactions to occur is the concentration of the reactants and is the collision of these molecules. Because if a molecule collides, it's going to react. Not the case for an overall reaction, because remember, an overall reaction, we can have several different things that we don't necessarily see going on. But for an elementary reaction, it can't be broken down to any simpler, all right? And so the only thing that's going to limit this reaction occurring is that the molecules running into each other. And so based on that, we can actually start coming into and looking at my rate laws just from a balanced chemical equation. All right, so let's start writing the rate laws for these. And so for this first one, for my unimolecular, essentially it's going to be my rate. I'm just going to abbreviate with R equals some reaction constant or rate constant, and then I would just have A. And it would be first order because the coefficient here is 1. Now, if it was 2A, it wouldn't be unimolecular, right? It would be bimolecular. And so let's take a look at that one. For this one, I've got A plus A, or essentially I've got 2A. And so my rate for this one is going to be the rate equals my rate constant A squared, right? It should be second order with respect to A because all I do for writing a rate law for an elementary reaction, and this is the key thing here, guys. Remember, I'm looking at elementary reactions here. Writing the rate law for an elementary reaction is only based on the molecular coefficient ratios, right? And so let's look at the next one. I've got A plus B, and so my rate is equal to the rate constant and then the concentration of A times the concentration of B. So it's first order to both of them because of the coefficients here. And then just for fun, let's take a look at these last ones, the termolecular ones. Notice I've got 3 A's here, so that's equivalent to 3A. And so my rate is going to be equal to some rate constant times the concentration of A cubed. So in that case, it would be a third order reaction. And now you should kind of start to understand why we don't really study our third order reactions, because they don't happen very often, because it's not very often that we get 3 different things running into each other, right? To actually with enough energy or enough orientation factor to form a product. And then the last one that we'll look at here is going to be this. Now this is essentially 2A plus B, and so the rate of this would be the rate times my rate constant, A squared, and then concentration of B. And so that one would be a little bit more likely to happen, but not so much. But this is going to give me my third overall. reaction order, it's going to be second order with respect to A and first order with respect to B. And again, remember, we can actually just look at a balanced equation and come up with a rate equation or a rate law for elementary reactions because they are only based on concentration, right? Whether or not the reaction happens is only based on concentration. This is not the case with overall reaction, guys. I can't stress this enough. There's a difference between an elementary reaction versus an overall reaction. You need to make sure that you distinguish that in your head, right? And you need to understand why we can just look at a balanced equation for an elementary reaction and come up with a rate law, and why we cannot do that with an overall reaction, right? So make sure you get that clarification in your head so that you're not confused as we move on. All right, and then the last thing, again, I kind of hinted on this earlier, but we're going to start looking at rate determining steps. And so essentially it's the slowest elementary reaction, and it limits and determines the overall rate. So an example here would be that I've got a first elementary reaction. So my first elementary reaction is fast. My second one is slow. And so what we can do is we can actually write two different rate laws, right? The rate law for my fast one would be my rate is equal to A times B, right? And so I could say that that's the rate law of my overall reaction, but it's not, because remember, this is the fast. It's not going to determine the rate of my reaction. This guy will. So my slowest elementary step will determine, because it's the bottleneck. Once everything gets past that, it should be consumed or form whatever is necessary faster than anywhere else. All right, and so now I'm going to look here, and my rate of this one is going to be equal to some K times concentration of C times the concentration of A. And so there's an issue here. Notice my rate laws need to need to agree with my overall equation, and I can't have this rate law for this reaction because there is no C, right? If we look in my overall reaction, I don't have a C as a reactant, therefore I can't have it in my rate law. My rate law has to agree with my overall reaction. And this is going to lead us into part C, section 5.A, where I'm not going to spend a whole lot of time working this kind of stuff. I'll do some sample problems for you, but to explain this on a lecture over just a recorded video, it's not the best way to do it. I need you to go ahead and take a look in your books at page 625 and 626. And what this is going to do, and actually 624, 25, and 26, and this is going to explain to you how to solve this and how to get rid of this C, because that's what we want to figure out in 5.6a is how do we get rid of the C? How do we make our overall rate law agree with our overall reaction, and even though we're going to base it on elementary steps? Okay, and so that's it for now. Again, big thing here in 5.6 is looking at what's an elementary reaction versus an overall reaction. What's a rate determining step or a rate limiting step? How come I can actually just write rate laws based on balanced elementary reactions? Make sure you understand that, and move on to 5.6a and be ready to work out the type of problem that we run into here at the end. And I will post some sample problems on this, so look for those.